So welcome to my talk, and thank you for being here. So my talk about hijacking Zen virtual machine for fun and profit. And actually, the technique I introduced to hijack virtual machine work with almost all kind of virtual machine. So actually, it doesn't only work on Zen. So that's why I put Zen in open and closed mark here. So my name is Nguyễn Anh Quỳnh, and you can call me Quỳnh here. So, okay, here's the motivation behind my talk. So usually, virtualization promise better security for the people who own the virtual machine, because usually you might think that you are safe inside your virtual machine because the other guys on other virtual machine cannot interfere with your virtual machine. So actually, that is not true, because the real power stays in the side, on the hand of people who own the physical machine. So in my talk, you can see that what can we do with good or bad intention if we have the control of the host virtual machine. So in this talk, we explore some technique to dynamically inject code into running virtual machine to hijack its execution. And after that, we can inspect and capture sensitive data. So in this talk, I focus on Zen, but it works with other kind of virtual machine as well. So this technique can be done quietly and secretly without awareness of the virtual machine owner. And it requires absolutely no modification to hijack virtual machine or the underlying hypervisor. And everything is implemented in user space, so it's very easy. And it works with all kind of operating system, be it Linux, BSD, OS, or Windows, or anything. Okay, so here's my agenda. So at first, I introduce something about Zen virtual machine and Zen debugging technique. And after that, I introduce the hijack virtual machine, Zen virtual machine technique. And because the technique can make the system a bit slower, so we might have some performance, so you can see how much is slow. And in the talk, I have some demos. And if I have some time left, I will discuss how to detect and anti-detect the hijacking technique. Okay, first part. So I suppose that people here, everybody heard about Zen. So yeah, Zen is kind of virtual machine, and it allows us to run multiple virtual machines on the same physical machine. So as in this picture, you can see that on top of the hardware, we have a thin layer of software named Zen Virtual Machine Monitor, or we also call it hypervisor, Zen hypervisor. And on top of the hypervisor, we have multiple virtual machines running at the same time. So in Zen terminology, we call virtual machine domain. So we have 4 domains running here in this picture. And Zen classify domain to 2 types domain. The first one is domain 0, the left one here. And the other type is user domain or domain U. And remember that domain 0 is kind of special privileged domain, and from domain 0 we control all the other domains. For example, you can from domain 0 you can start as a domain, stop as a domain, pause, resume, do anything else. And maybe you already know that Zen is already in Linux kernel, and in the current version you can run Zen from Linux. So I think in the future it will be very widely spread. Okay, something about debugging on Intel. I think this one is familiar to everybody here. So on Intel, they provide some facility for debugging. The first one, you can single step your program by your debugging tool. For example, after single step means after each instruction, your debug program is paused. So your debugger can come to inspect your program. And you can turn on the single step mode by turn on the TF flag in eFlag register on Intel. And when the after each step, after each instruction, the interrupt one is triggered. The other facilities is interrupt tree. And basically, when the program hits the CC instruction, which is a breakpoint instruction, the interrupt tree is triggered, and it will notify the debugger to come to inspect the program. So yeah, Intel has 2 interrupt for debugging. Okay, so here's how debug is handling in Zen. On the first case, when a breakpoint, the CC instruction is hit in Zen, one exception is raised. And we switch from the virtual machine down to the hypervisor, to the Zen layer. And the hypervisor will check to see if the virtual machine which hit the CC is in user mode or not. In case the virtual machine is in user mode, it return control back to the virtual machine and let it run normally. But in case the virtual machine is in kernel mode, then we pause that virtual machine for debugger, for example, for ZDB, come to inspect. And that's how Zen handles the interrupt tree. And the interrupt on is handled in a similar way. Okay, the next part. So how to hijack Zen virtual machine. So here's my assumption. Somehow we have the control but domain 0. You can be a real owner of the virtual machine, so we have control of domain 0. Or you are the attacker, somehow you break in the virtual machine and take over compromise domain 0 and you have control of domain 0. But anyway, we have the control of domain 0. That's the assumption. So what can we do? We own the other virtual machine. So we control this one. And what can we do with the other virtual machine running on the same physical machine here? So in my talk, I show you that we can hijack the other virtual machine as a domain U. And you can do it silently and quietly. And after that, we can extract sensitive data from hijacked virtual machine. Okay, so here's the first demo for your pleasure. So in this demo, I will hijack the virtual machine and capture on the SS username password. So here's the demo. So I'm running Zen on my machine now, and actually we are in domain 0 now. So let's see which virtual machine is running now. So you can see that we have 2 virtual machines. Domain 0 and the other virtual machine is named Etsy. So now from domain 0, I will run a program. And this program will inject only 1 byte into Etsy. Etsy is a Linux virtual machine. And inside Etsy, we have a secure shell service. Okay, so we try to connect to Etsy here now. Secure shell to Etsy. Enter my username. Actually, my username is Queen here. So now I enter my password. Okay, I'm in. So inside Etsy, you have secure shell service running. Okay. So now, okay, quit. Now inside domain 0, I run 1 program, and this program inject 1 byte, only 1 byte, into Etsy. And we can see, we can do something very cool here. So watch the left window, the domain 0 window. Now I try to connect to Etsy. Can you see? Immediately I capture the username. Enter password. Okay, that's an easy password. Let's try again. This time I connect with another ID, DeepSeek. DeepSeek. Okay, DeepSeek is trying to connect. You see it? Password. Yeah, again, very easy password. Okay, so that means.
But you have to run this code from out of the domain from the example.
Sorry?
You have to run this code from out of one of the domains of the example.
I run the program in domain 0, and I capture all the username password inside the user domain.
You have to have control of domain 0.
Yeah, that's my assumption in the last line. Yeah, here's my assumption. I have control of domain 0. So how to do that? Here's my offer. If anybody here can tell me how the last demo work, I can buy you a beer. Okay, now I explain something about how the technique works. So here we try to hijack a virtual machine, and to do that, actually I try to employ the Zen debugging infrastructure to hijack the virtual machine execution. And to do that, actually what I did is I inject a breakpoint, a software breakpoint into a running virtual machine, and together with the breakpoint I have a function. So we have a couple breakpoint function, and I call it a probe. So I try to inject probe, which consists of one breakpoint and one function. And the function is also called probe handler. So here's the technique. So I inject a probe into the kernel space of the virtual machine. And together with the breakpoint, you have a probe handler running in domain 0. And whenever the breakpoint is hit here, the switch, as I explained in the last few slides, we switch back to the Zen hypervisor, and Zen hypervisor will notify our probe handler inside the user space domain 0. And here we run the probe handler, which is a function, and this probe handler will connect access to the user domain here and extract the information out. And that's how it works. Very simple. Okay, yeah, that's how it works. We inject breakpoint into the right place inside the virtual machine, and with each breakpoint, you have a probe handler, and the probe handler will be executed when the breakpoint happens. Okay, so there's some implementation issue in the technique. It's not that trivial. The first one, where to inject breakpoint. Because inside the kernel space, there are many places you can inject breakpoint, but the question is where to inject breakpoint. So you can do it by, there are three ways to do that. At first, you can look into the kernel source code in case the OS has kernel source code like Linux, for example. So if you compile the Linux kernel with debugging information, you can extract many information from the kernel binary. For example, you can know that the virtual address corresponds to this particular line of this particular file in the kernel source code. You can have a lot of information like that. And of course, another way, you can also reverse the kernel binary, and you can check the assembly code to know where to put the breakpoint. And the other way, easy. You can look at the kernel symbol file, which comes with the kernel binary. And in Linux case, that is a system.map file. Okay, that's how to inject breakpoint. There's a problem. When you inject software breakpoint, which is a CC instruction, into the virtual machine memory, of course you override some instruction, right? CC is 1 byte. So by injecting that byte into the virtual machine, you override one instruction. So of course you have to somehow save that instruction and execute it later after we hand the breakpoint. So there are two ways to hand the breakpoint event. And I propose here two schemes. The first one is inline scheme, and the second one is outline scheme. What is inline scheme? It's very simple. I call it inline scheme because I execute the instruction. I call it the original instruction, which is overwritten by CC in the original place. So inline scheme executes the original instruction in the original place. So here's how it works. In the preparation step, we just suppose that we override the CC into this instruction. So in the preparation step, we copy this byte to another buffer, which I call inline buffer. And then I write CC here. So when the virtual machine executes and it hits